Thanks for organizing this fantastic conference, and thanks for organizing it in a place that I don't have to travel very far to get to it. It's really nice. I appreciate it. So I'm gonna sort of describe what the project is. I think a lot of people in this room will already know some of this stuff, so I hope I won't bore you. But I wanted to sort of describe what the project is. That is to say, why it is that one wants to think about physical structure in arithmetic in the first place. What's going on there? Why are we even doing that to begin with? And then I want to sort of try to address the principal problem with that, which is trying to make anything precise. I'll start off with just the sort of overview picture. This is a very broad stroke picture. So I think sooner or later everyone will wince at something that I have to say. So just go ahead and wince. I should also say that I'm going to use some physics terms, and I'll probably make mistakes, and I hope that you will help me improve. I'm not making mistakes because I'm careless. I'm making mistakes because I'm ignorant. So I'd like to learn more. But I first just want to sort of give the overview of the picture here. So what's the picture? So let's start off by talking about spec of the integers. So when you first take an algebraic geometry class, you learn about spec of the integers, and the first thing that you learn is that it's the set of prime ideals of Z along with the Zariski topology. So, and then there's a sheaf of rings. We won't worry about that right now, but first I want to draw a picture of this topological space. So what does it look like? Well, you've got a big point. This is the generic point. This corresponds to the prime ideal 0. In algebraic geometry, unlike in things like manifold theory, in algebraic geometry, when you think about the functions on your object, on your geometric object, the values that those functions take varies with the point that you're defining it on. So if you have a manifold and you take a function on that manifold and you evaluate that function at a point, you get a real number. If you take a function on a scheme and you evaluate it at a point, you get an element of a field, but that field can vary depending on what the point is. So here, that field is called the residue field. And so here, the residue field is the set of rational numbers Q. Well, so that's a big point. Why is it a big point? It's because it's a generic point. So if I take the closure of it, then I get the entire thing. What else is in there? Well, there's all the closed primes. I guess I'll do these in purple. So that corresponds to the prime ideal 2, and the field, the residue field there is F2. And you have the prime ideal 3, and you have the residue field F3. You can see where this is going. There's a prime ideal 5, and you have F5, and this continues on. And the topology is such that, well, these are closed points. That big point has the property that if you take its closure, you get everything. And then the only other thing you need to know is that you can only keep finitely many of these closed points, these purple points, in focus at any given time. And those three sentences together tell you what the topology of this thing is. So if you're just learning about algebraic geometry, you might look at this picture and be a little disappointed because you were hoping to see some exciting arithmetic buried here, but it's not really here. It's just sort of, I don't know, there's not really a whole lot going on. It's a little bland as a picture. And you certainly can't see where anything that looks like a three-dimensional quantum field theory could possibly live. There's nothing here. But what algebraic geometry gives you, in addition to the Zariski topology, is it gives you a set of lenses with respect to which to look at these schemes. And this is just not a very powerful set of lenses. The Zariski topology is a very, very coarse topology. It doesn't know a whole lot of information. It's very weak on information. So we can refine it. We can move out to something that looks more like the Étale topology of spec Z. The Étale topology of spec Z, well, that incorporates everything you see here, but it also includes information about the absolute Galois groups of all these fields and how these things fit together, right? So, okay, so what kinds of things happen? Well, The absolute Galois groups, the absolute Galois group of Q is a big mystery. No one quite knows what it is. The absolute Galois groups of the finite fields, those are all pretty well known. There's Z hats, right? And then from the Étale point of view, there's nothing else going on there. So you have a pi1, which gives you a Z hat, and you don't have any higher homotopical information. So that tells you that what you're going to have here that lies over these purple points are going to be circles of some sort. They're profinite circles, but we're not going to let that bother us. Those are circles of some sort. And these circles are all embedded as closed inside some ambient space. What's the nature of that ambient space? Well, it turns out that it's three-dimensional, so I'm going to draw it as a box. And then, where's my purple guy? Here it is. And then, well, each one of these corresponds to a knot, and Sherry can draw the trefoil knot. I can't even draw that, so I'm just going to keep drawing the unknot. I'm not going to do better than that, sorry. So, you know, maybe this is the prime 2, this is the prime 3 here. Maybe it's linked, maybe it's not, maybe here's the prime 5, et cetera, et cetera, et cetera. You can draw these pictures. And so what you have is you have this tangle, you have this sort of, this link sitting inside some three-dimensional thing, some three-dimensional space, and you want to try and study these objects. Well, how do you study these objects? Well, one thing that you can do is you can start to thicken up these knots. That's usually a thing that you want to do. You want to thicken up these knots and then maybe look at the knotted torus that contains those knots. That's a good thing to do. That's how you can use that to study things like linking numbers and stuff like that. So what does that correspond to in this picture here? Well, if I thicken up these knots, that corresponds to taking the limit of z mod p to the n, which is also called ZP. Since moving to the UK, I've learned that people use this to mean the cyclic group of order P here. I don't know why they do that. These are the p-adics. You shouldn't do that. These are the p-adics. And so this is the solid torus that you get by thickening up these knots. That's supposed to be the intuition. And then, well, what are you supposed to do next? Well, you're supposed to take just the boundary of that thing. When you look at the boundary of that thing, then that corresponds to inverting P here. And so that arrives at QP. So this is, I'm not going to try and draw a picture of this because it's going to be even worse than that. This is a knotted solid torus. I'm just going to put this in quotation marks. And this is a knotted torus. Torus might make you think things that aren't true. There's no sense in which these things are orientable. These things are exceptionally far from being even vaguely orientable. They're very, very far from it.
Are we still talking about the Étale topology, or we've moved somewhere else?
Yeah, no, we're talking about the Étale topology. Yeah, that's exactly right. Yeah, we're talking about the Étale topology, and the question is, how do you know any of this stuff? Like, where do these numbers come from, right? I'm claiming that this is something like a surface. These things are knots. Well, I kind of gave you an argument for why these things are knots, because I said, well, there's pi1 is z hat, and there aren't any other homotopy groups, so that sounds pretty circly to me, so I'll draw a circle. But why should you be thinking of this as a surface? Why should you be thinking of the ambient thing as a three-manifold, right? Those are good questions. And the answer comes from cohomology, because that's the only thing that we have. So the answer comes from cohomology, and more precisely from class field theory, sort of incarnated as cohomology. And so what you have is you have two different duality theorems. Here's the sort of local theorem. The local theorem says that you have a two-dimensional Poincare duality on this space, on this QP here, or spec of QP if you like. And then, so let me say the global one here a little more precisely, just so we can have a look at it. So I like to write it in the following way. I like to imagine taking spec Z. We're actually going to compactify spec Z. Spec Z isn't compact. It's missing a point, and that point roughly corresponds to the Archimedean place. So we're going to add that in. And then when we look at the cohomology with certain kinds of coefficients, now this is like some form of Étale cohomology. If you press me on details, I will give you details, but I'm doing an overview here. then you have a perfect pairing between this and a certain dualizing object. And that perfect pairing is, well, you got to be careful. It's not valued in like the unit or something. It's valued in the circle. It's a Pontryagin type duality. The Pontryagin duality statement is identifying the Pontryagin dual of this with this. And so what is this F dual? There's no number 3 in this picture yet. Let me show you where the number 3 appears. It appears in the computation of this F dual, which is just from F to G and shifted by 3. And there's the 3. This entire picture comes from that 3 right there. The way you prove this is using global class field theory. Yeah.
R in front of it.
I'm not going to derive it. Everything is implicitly derived. Yes, I do want to put an R in front of it, but I'm not going to. Yeah, it's a derived. It's derived.
Sorry, for the superscript of your second H,
That's just minus star.
minus star.
It's just the usual way duality has to switch things around.
And there it's the usual circle.
What's that?
It's the usual circle.
It's the usual circle. Yeah. Regarded as a topological abelian group.
Okay,
Or a
but
picnotic abelian group, if you like such things.
classically before picnotic stuff, we just use the Q mod Z inside of it, right?
Yeah, that's right. Classically, before you could really do topology and algebra at the same time, you use two months out, which is
And
fine.
the thing is that like GM is divisible and therefore it's just normal Hom. Right?
Well, I
You
mean,
take normal harm, and you take the flat common.
Sure. Okay, fine.
okay, so this is and where does this come from? This comes from global class field theory. This is a consequence of global class field theory. Suitably. So the point here is that the way in which you understand this geometric picture comes from a very small amount of information in some sense. It comes from, well, the presence of a geometric object, something where I can take sheaves, roughly, and the category of sheaves over them. All of the information in this picture is actually contained in the category of sheaves on these things. The sheaves that you write down have to be quite sophisticated in order to get this to really work, but that's where this story comes from. Now, another objection that you can lodge to this whole story is the fact that, well, you know, I just said that this thing is supposed to be a knotted torus, right? I'm supposed to imagine like something that looks like a Riemann surface inside this 3 manifold. Okay. Well, if you try to imagine something that looks like a Riemann surface in this manifold, the first thing that you're probably going to be able to do is you're probably going to be able to imagine that it could have distinct points. Right? But if I talk about spec of QP, QP is a field. If I take spec or spoof or whatever fancy version of SPO you can think of QP, I'm going to have a 1-point set. So there's something kind of weird about declaring this thing to be a knotted torus. We're doing it because the cohomology exhibits a 2-dimensional duality. But there's nothing in QP that tells you that that's going to happen. There's nothing in thinking about spec of QP that suggests that that's actually going to take place. I can have the same objection about spec of FP for that matter. So, okay. So when we draw this picture, we do draw up a picture, and it's a very convincing picture in some ways, but it's also not that convincing, right? Because in some sense, we would like to have a stronger kind of topological story here. Well, we have one in the case of QP. In the case of QP, we now have what's called the Farg-Fontaine curve. I'm not going to get into the details of what the Farg-Fontaine curve is. It's a little complicated. It's a moduli space of untilts up to Frobenius. So you have to move into a perfectoid context in order to write it down. It's a rather exotic object, right? It's not something that you write down as, you know, a topological space with a nice sheaf of functions or something that you write it down in a kind of peculiar way. but it does exist and it does have distinct points. And the first thing that Fargan-Fontaine proved about it is that you can indeed prove local class field theory with it. And so that allowed you to, so that's the local version of this statement, which then corresponds to a two-dimensional duality that you see on this thing. So, okay, so we start to have a little bit of information here. We have a little bit of information about what the geometry of these things looks like. But consistently, the information that you're actually able to use in these stories is the same. You have some category of geometric objects. So this is some category of, I'm just going to put this in quotes, geometric objects. And then for each object of this category, what you have is you have an associated sheaf theory. You have an associated category of sheaves that you can talk about. And this is it. This is all you have at your disposal. By the way, this AX here, technically speaking, what kind of thing is it? Well, it's a sheaf of symmetric monoidal categories, or symmetric monoidal infinity categories, if you like. This is what you have access to. Everything that we want to say about these things comes from just this amount of data and nothing more. So you have some objects that you've decided that you want to call geometric, and you have some theory of sheaves on those objects. And what you mean by sheaf doesn't really have to look much like what we know of as sheaves, right? We can be quite exotic about what kinds of things count as sheaves. These are just really just a collection of categories that satisfy some locality property. That's all we're really asking for here. Yeah.
It's supposed to be like sheaf abelian groups, and the monoidal thing is the tensor product.
Yeah, so I mean, you can think of, for example, if you think of X as the category of schemes, then this thing carries any scheme to its category of quasi-coherent sheaves.
Okay, yeah.
Or you can think of it going to its L-adic sheaves.
So not like sheaves
Or
of
you can think of it
sets.
as going to the D modules, or you can think of it as going to, there's all these different categories of D modules that you, or of sheaves.
Linear
that you can
sheaves.
write down. And so that's what sheaf means here. But you can get quite aggressive with how weird these sheaves get, right? This notion of sheaf can be pretty weird. So, okay, well, I mentioned that this is a result of global class field theory. Global class field theory is supposed to be an abelian version of a more complicated statement, which is the Langlands duality. And there's a local Langlands duality and a global Langlands duality, and they're supposed to fit together. I'm not going to get into these details because I don't know enough, and I probably couldn't do a good job of it. But what I will say is that you can start to ask, well, how are we ever going to get more purchase on these geometric objects? How are we ever going to be able to state more complicated theorems that are going to show us the sort of finer structure of these things? Another way to ask the same question is, well, what kinds of knot invariants, we learned about knot invariants from Jerry this morning, what kinds of knot invariants can you write down about these things? And once you've written them down, how do you hope to study them? So in low-dimensional topology, there's this bevy of wonderful knot invariants, and a whole lot of them come from contemplating physics. They come from contemplating gauge theories. So the goal becomes, well, to what extent can you do physics on this thing? What extent can you define a quantum field theory or a gauge theory on this thing? What would be the benefit of such a thing? Well, for example, if you do the same thing with a Riemann surface and you try and understand conformal field theories on a Riemann surface, then there's this really beautiful program to prove the geometric version of the Langlands conjectures by effectively taking these. You have a comparison, a local comparison called geometric Satake, and then you're going to integrate that comparison over the entire Riemann surface, and that will actually give you the global geometric Langlands conjecture. So the theory goes. So you could ask, can you do the same thing on the Farg-Fontaine curve? This is now our analog of a Riemann surface. Farg and Schulze have shown that you can actually write down the local Langlands conjecture as a form of geometric Langlands on this exotic object. So then the question is, can you actually make the program that works or appears to work in geometric Langlands, can you make it work here? And once again, that'll come down to trying to do some sort of physics on this object here. So all of this is supposed to be motivation for the following objective. I'm not sure if it is motivation for you, but it was motivation for me. Goal. Do physics on spec Z somehow, or some compactification of it or something. And well, again, the situation is that the only ways in which we have to understand this object are in these kinds of terms. So if I think about some of the ways that we have to do physics to sort of formally write down physical theories in mathematics, well, there's sort of two principal ways to go about this. On the one hand, you can try and keep track of the spaces of states. This is the Schrodinger approach, if you like. And this is what gives rise to the sort of Atiyah-Siegel axioms for a QFT. What do these things look like? Well, roughly speaking, what these things look like is that you're writing down a functor, and that functor, the source of it is some category of cobordisms. And you're looking at a symmetric monoidal functor from this thing into, well, I don't know what, some category. You can be vague about that. So it's not going to be important here because I'm already having trouble back here. I don't know what the heck a cobordism in this funny world could possibly mean. I don't have a definition for that. What on earth could it mean to take a boundary? Not at all clear. You can write down a few examples that seem promising, but it doesn't seem clear how you could ever write down a cobordism or even a cylinder. It's not at all clear how to write down cylinders in this context. There's just nothing available that looks like this. So I don't know how to do this. I'm not ruling it out, but I have no idea how to set up a story like this. So there's the other approach, which is to contemplate observables. When we contemplate observables, this is more or less the Heisenberg point of view on quantum field theory. And so then what you end up doing is you end up studying the algebra of observables in your favorite quantum field theory. This is what gives rise to factorization algebras. And maybe I better put some names here. So, of course, Kevin Costello and Owen William wrote the sort of tract that identifies these things in quantum field theory. Before that, we had the sort of slightly earlier variants due to Bailenson and Drinfeld. And then, well, in a more topological setting, God, there's a lot of names that I want to write down here. So then there's Ayala, Francis, and Lurie. Worked on various editions of the notion of a factorization algebra. This, in some sense, is a sort of version for manifolds, as we know and love them. This is a sort of edition that is trying to do this for complex algebraic varieties. Actually, they were focused mostly on complex curves. Francis and Gates-Gorey then sort of generalized it to higher dimensional complex algebraic varieties. And these are basically, I want to think of this as the sort of homotopical context. Although I guess actually Ayala Francis have an even more broad program soon, but let me think of just that version. So, okay, so how do these factorization algebras work? So let me draw some more pictures. So the way these factorization algebras work is that you've got your space-time manifold. I guess it looks like that now. I don't know what that means for us, but there you go. And you have an open set U, and you think of the space of observables at U. So that is to say, you think of the space of ways of pairing your measurement system with the quantum mechanical or quantum system that you're studying. Well, of course, observations interact with the thing that you're studying. So if I wrote down another V here, then I wouldn't be able to combine the observations that I made in these two regions. Like there'd be interference. This is a picture of the two-slit experiment. But if I made V different from U, separate from U, disjoint from U, and I embedded these things in sort of a common W here, then if I look at the observables for U and the observables for V, maybe these are complex vector spaces. Then you'll get an induced map into the observables on them.
Sorry, is this supposed to be like space-time or the state?
This is space-time. So, this is the rough idea here. And there's something kind of critical that's going into this picture, and it's something that I didn't understand what the name for was, but I guess there's a couple of different names I could use here. So one is the cluster decomposition principle. I learned this from people in this room, actually. Right. Oh, I can't find you now. Oh, there you are. Hi. The cluster decomposition principle. And what's the idea behind the cluster decomposition principle? Well, it's that if you're doing an experiment in your hometown, wherever that might be, London, let's say, and I'm doing an experiment here in Edinburgh, then the results of those two experiments shouldn't interfere with each other. That had better be true, otherwise experimental physics isn't going to work. Right, because then you'd have to know, in order to predict the outcome of an experiment, you'd have to know what was going on in the entire universe with every single particle. That's not going to work. We got to.
This is not true for theories. It's true for massive quantum field theories, but it's not true for continuum field theories.
That's right. That's right. But I am interested in it, and it is what's relevant for this story here. So, in particular, you really need to know what you mean by distant in order to have a working theory here, right? You need to be able to say that you can say that U and V are sufficiently distant that they won't interact with each other. That doesn't sound like much, knowing whether two things are distant. That doesn't sound like a lot of information. But I claim it's actually quite a lot of information. So there's a joke that I tell every time I talk about this, and no one has laughed yet, but I'm going to tell it again. And I don't expect laughter. It's okay. I've come to expect it. And the joke goes like this. So there's a physicist and a dyed-in-the-wool homotopy theorist, and they're talking to one another. And the physicist says, all right, well, now let's contemplate the real line. And the homotopy theorist understands this immediately and says, okay, good, I'm considering the real line. Thank you. And the physicist says, now, okay, consider a point on the real line. And the homotopy theorist has agreed. Yes, I understand. That's what I can do. I understand completely. And then the physicist says, now consider another point. This is the first time anyone's ever laughed. So for those of you who aren't laughing, me explaining the joke is not going to make it better, but it's usually a way to kill a joke. But see, the homotopy theorist, when they look at the real line, the homotopy theorist doesn't see a whole lot of points. The homotopy theorist sees the real line as a contractible space. So if you've chosen X, you've chosen the only point there. Homotopy theorists don't acknowledge the existence of other points, that there's nothing meaningful about them. So homotopy theorists couldn't possibly identify the difference between these two things. So why is that relevant? Well, it's relevant because there's a version of these factorization algebras where you put into it a manifold, and then you look at the locally constant factorization algebras on that manifold with some coefficients. And what are these locally constant factorization algebras? Well, it's just exactly the data of a bunch of maps like this and a bunch of coherences that control them. And then I'm additionally going to have the rule that once you make these things sufficiently small, there's no difference in the observables, right? So if I take this U here and I wiggle it just a little bit, I don't expect to have any change in the observables, right? So these correspond to field theories where the metric is just not going to be relevant, right? And so these things are roughly capturing topological quantum field theories, at least capturing the observables of a topological quantum field. So these locally constant factorization algebras, homotopy theorists have actually been thinking about these for a long time under different names. So if you look at a locally constant, factorization algebra on Euclidean space, on just Rn, with values in something, I don't care what, then, so these values, by the way, those are just the category in which these observables live. That's all I mean by that. Well, what are these things? These things turn out to be the same thing as EN algebras. So homotopy theorists have been studying these because they were interested in trying to find out which homotopy types are the n-fold loop spaces of other homotopy types. So for two completely separate reasons, they've sort of converged on these same things. And then, well, there's a nice sort of locality principle that you can use here. And that locality principle says that, well, if you've got a complicated manifold, then you can break it up into pieces. And then on each of those pieces, you can understand the locally constant factorization algebras there and then glue the whole thing together. So understanding that these things are EN algebras, now if I've got an N manifold, then I can think of a locally constant factorization algebra as a sort of continuously varying family of EN algebras over that manifold. Now, one thing that sticks out to you straight away is that this makes it obvious that this is not a homotopy invariant construction. It depends on the N, so it better not. So you can ask a question, and as a homotopy theorist, I find it an interesting question. But I think it's also an interesting question because it spurs an answer to a broader question, which is how are we ever going to do physics on something as abstract as this? And so here's the question that I can put forward, which is, maybe it's less of a question than a demand. Please refine the homotopy type my notation for homotopy type is pi infinity. So if I've got a manifold M, I want to refine that homotopy type by adding some extra structure to it, such that it suffices to reconstruct locally constant factorization algebras on M. We've just seen that the raw homotopy type alone isn't going to cut it. It's a clear example. But then the question is, can I add more information to that homotopy type in order to see these locally constant factorization algebras? So I want to emphasize that if you're just trying to think about homotopy types, well, you do have a notion of sheaves on homotopy types. We have locally constant sheaves. Locally constant sheaves are basically just functors out of the homotopy type. You know, this is monodromy when you think about locally constant sheaves of vector spaces, and you set out on your manifold and you drive with your arm out of the window and you've got a section of your favorite vector bundle. And as you drive, you come back and you discover that you've got a different section, and that different section corresponds to a representation of pi1 on the stalk of that sheaf. So we're doing exactly the same thing here. I want to think about the homotopy type of this manifold, and I want to refine it in some way so that I can have a similar formula for locally constant factorization algebras. So I've got an object which I want to consider as vaguely geometric. This is really vaguely geometric now, right? I mean, I don't even notice that there are two different points on the real line. I have a very vague notion of geometry here, but I also have a functioning notion of sheaves, in the sense that it's a functor like this. And the question is, can I do some sort of uniform construction with this that will produce locally constant factorization algebras in this case, and then give me something that would be a reasonable theory of factorization algebras in all these other sort of exotic arithmetic settings that we were talking about? So I've motivated the story by talking about arithmetic, but I'm in some sense motivating the solution by talking about homotopy. I guess that's sort of reflective of my whole disposition. Okay. So now I'll tell you what the proposed answer is. Are there questions? That's sort of the first half. Is it clear why I'm doing this?
No.
Someone say no?
Yes,
It's not clear why I'm doing this?
yes, it's not clear.
Okay.
Seems to me.
Um. What can I help you with?
Well, for one, I'm wondering like what would want to achieve by such a instruction, like doing physics, quote unquote, on spec of Z.
Well, let me answer it for spec of QP. Will you let me do that?
Sure.
And I can give you a very precise answer. So there's this strategy to geometrize local Langlands by turning what the story for geometric Langlands over a Riemann surface into a question about this exotic Farg-Fontaine curve, right? And the biggest, most promising strategy, maybe it's even already a successful strategy. I'm not sure what the status of the literature is. David's here, so he can tell me. The strategy is that you have a local statement, so near. I can also only draw Riemann surfaces of genus 1 or 0, so that's another limitation. And the idea is that near sort of these points, you have a certain equivalence, which you can write down, which is a sort of local version of that equivalence, which is proved. It's geometric satake, as it's called. You want a slightly refined version of that, which is kind of hard to state, but you need a version of that. And then you need it as a factorization algebra. You're going to have an equivalence of two categories, which are themselves factorization categories, as these points move around this thing. Then you're going to integrate over this entire thing. And the claim is that will be the geometric Langlands equivalence.
Also not locally constant factorization.
They're not locally constant factorization algebras.
You're going to talk about non-locally constant?
I'm going to talk about everything. About every kind of factorization algebra I know anything about. Oh, that's not true. I did say quite a lot of generality. That's not true. I don't know how to talk about a beta form of factorization homology. So I can only talk about the alpha version, if you know what I mean by that. In physics language, I'm only going to be able to talk about what happens for point observables. I don't have a theory for you yet for more complicated kinds of observables, line observables, and those sorts of things. It feels like I ought to be able to get one, but I haven't gotten it yet. So let me keep my statements honest. But other than that, I'm going to say about it, I'm going to try and give you a formalism that will reconstruct all forms of factorization algebras I know something about. Are you motivated yet?
I am motivated, but I'm wondering what kind of object are you, like what kind of Lagrange correspondence are you trying to construct in like over Z or Q? Like what is the global thing here?
You want to know what global Langlands conjecture says?
Okay,
I'm sure there are people in this room that
No,
can tell you this way better than me. I'm not the person to ask this question.
okay, thank you. Thank you.
I'm definitely the wrong person to tell you what that is because I'm way out of my depth with that. Okay, so all right, I'm going to assume that you're still motivated. If you lose motivation, though, you tell me.
Sure.
All right, so here's the solution to this issue. So I'm going to start off with understanding this principle, this cluster decomposition principle, in concrete terms. So the issue is that if you've got a manifold, the one thing that you know is you know what it means for 2 points of that manifold to be distinct. Well, you know other things than that, but you at least know that. So I want to codify that piece of information. And so I'll do that by first defining a category I like to call D. This is a category of finite sets and inequivalence relations. Inequivalence relations. I hear you asking, what's an inequivalence relation? Well, it's the complement of an equivalence relation. But now I hear you asking another question, which is, what's the difference between that and just giving me the equivalence relation? And the answer is nothing, but this is a category. So in this category, the maps are going to preserve the inequivalence, not the equivalence. Or another way of saying it is that the objects here are sets, finite sets with an equivalence relation, but the maps are going to reflect the equivalence rather than preserve it. Okay, so this is the category D. By the way, I've given this talk a few times now. So far, no one has been able to tell me that they know a place in the literature where this stupid category is used. I find that really hard to believe, but so far I haven't seen it used yet. If you know a place, please tell me. I'd be interested. Someone told me it might be in a paper of Borchards, but I couldn't find that. So
Equivalence relations are morphisms somehow?
No. The objects are finite sets equipped with an inequivalence relation. And the morphisms preserve those inequivalence relations.
2 points are distinct,
They remain distinct after I pass through. So for example, let's look at this.
Which are the same, they might become different.
That's right. So here's a finite set with 6 elements. There are 3 equivalence classes, right? This is different from these 5. These 2 are different from these 4. These 3 are different from these 3. This is an example. This is an object of D. Let's write down a morphism of D. Well, I'll take these two elements here and I'll identify them. That's a nice morphism of D. Perfectly legitimate. Here's another morphism of D. Well, I can just take the set with 6 elements in one big equivalence class. Right? No 2 things are distinct in this story. And I'll just use the identity map to go from here to here. And I've sort of broken up 6 into these sort of chunks, right? I like to call these dispersive maps. Because you think of taking the set with 6 elements in a nice cluster here, and you're going to spread them out in a certain way. I'm going to spread 1 over this way, 2 over this way, and 3 down this way. And so I'm going to spread these things out. So these are the dispersive maps. Happy? This is the category I'm going to work with. And now I want to tell you what the structure is that I need. I'm going to answer the question I'm erasing. Probably not good form, but that's what I'm going to do. And what's the structure that I'm going to need? So you've got this category of geometric objects. It's something, right? It can be very, very, very abstract. And what I'm going to be interested in, I'm going to be interested in what are called isolability objects in this category. So an isolability object of X, well, is a functor W dot, which is going to go from the opposite of this category D to X. And in this funny notation I've been using, I like to write it like that. And this thing needs to satisfy some properties. Actually, it needs to satisfy infinitely many properties, but I'm just going to write down the first one for you and then let you imagine what the rest of them look like. Unless you force me to write them all down, in which case I guess I'll have to concede. So, but let me motivate what the condition that I'm going to write here is. So if we go back to these inequivalence relations, well, then let's think about what happens. So suppose that I've got 2 elements of an object of D, and let's say they're inequivalent. Then if I find a new object of that D, well, then Y will have to be inequivalent to X, or Y will have to be inequivalent to Z, or perhaps both. That's the cotransitivity property that you have from taking the complement of an equivalence relation. Okay, so I want to codify a version of that works here. And what's the version of that? Well, if I look at this is the set of, morally, this is the set of pairs of points that are distinct. You should think of this as something like the complement of the diagonal. And then if I introduce another point, so let's call this point X and this point Z, and this is a new point Y, then, well, Y has to be either different from X or different from Z. So how do you write that down? In this language, you write it down like this. Others that look like this too, that involve the higher ones. So if you have X, Y, and Z, and X and Z are different, then Y either needs to be different from Z, or it needs to be different from X, or it needs to be different from both of them. And there's a version of this that works for any kind of, there's a much higher version.
What is the right hand side? What is this?
This is a push out. Nobody ever does this.
Put the push out on top. I mean,
Yeah, am I the only one that does this? I'm worried that I'm the only one that does this. I've been doing this for years. Well, anyway, yeah, I put it because that's where if I'm pushing it out, it comes from up here. Right? Down here, no one's pushing up. I'm pushing...
Wait, sorry, this is the union inside there?
Yeah, this is the push out, right? This sits inside here. This sits inside here. This sits inside here. Then forming the push
Oh,
out.
thought they were in.
Not the symbol that y'all are using. What am I supposed to be using here?
Put it underneath.
I'm gonna put it underneath. It's madness. I'm refused. No. I'm right. No, it's the children who are wrong. Okay, so this is the notion of an isolability object of this category.
Can you give us an example? Let's say.
I'd love to. Thank you very much.
So W 1+1 is not necessarily.
Let me answer one question before I can ask another one. You can't stack them. That's not gonna. All right, so suppose I've got a manifold. All right, what am I gonna do? I'm gonna turn it into an isolability manifold. This is a functor from D op to like manifolds. And I'm gonna do probably what you're guessing I'm gonna do. I'm gonna look at the set of, maybe I'll say it like this, these are maps from lambda to M such that if I is inequivalent to J, then the corresponding coordinates are unequal.
So you're treating manifold as an ordinary category, or is it, are these homotopy pushouts in some?
Yeah, there'll be homotopy pushouts if I'm in an infinity category, and there'll just be pushouts if I'm in a one category.
And here you're treating manifolds as a one category.
Yeah, manifold is a one category here. Yeah. Yeah, it won't change much.
But a manifold also has a natural inequivalence relation.
Yeah, manifolds are nice because they have underlying sets, right? I'm using that here to my advantage. That isn't something I always get away with, right? Homotopy types don't actually have underlying sets in any strong sense. I mean, you could like pi 0, but that's just lame.
Right. Have you managed to find very exotic isolability objects on manifolds?
Yeah, well, suppose that you did something like this. Suppose I looked at maybe this is a fibration or something nice, a nice map from M to N, but not an injection, importantly. Well, I can write down an isolability object that I like to call MF dot. And here, maybe I'll just tell you what the sort of punchline is. I'm going to regard X and Y as different if and only if, their images are unequal. So if and only if they lie in different fibers of this map. This is nice because, well, you don't have a functor. This thing here doesn't provide you with a functor from manifolds to isolability manifolds. Instead, what you have is a functor from manifolds to spans of isolability manifolds. And this is the thing that sits in between, right? So if I've got M and I've got N, then MF actually lives here. The kind of thing that you get when you start thinking about these things. This is because not all maps of manifolds are injective.
It seems that's a special case of just a manifold with an inequivalence relation. That
Yep.
might not be the usual one.
Yeah, indeed, it is. Yeah, so manifolds with inequivalence relations, at least if the inequivalence relations are reasonable, give rise to something. Absolutely. Yeah, there are a lot of these. It's a big old category. Now, you can also get other versions of this. So for example, you can, if you have something in Minkowski signature, right, then you can ask for space-like separated points. You can declare those to be different. That would be another interesting example of these things. Okay, how am I doing? All right, so I have this category of geometric objects, and now I'm asking for some additional piece of structure. The additional piece of structure is this isolability structure. And once I have that, you can ask, well, what can I do now, right? How can I get to something like factorization algebras? So the claim is that I can define now factorization algebras on an isolability object of X with coefficients in this sheaf theory that I've got. And it will recover known versions of factorization algebras. That's the claim. That's, if you like, that's the theorem of talk. It's not much of a theorem, but it's what I've got. So the question is, how do you define this thing? So here's how you define this thing. So let me first sort of tell you kind of morally what the objects are. So the objects are a bunch of information. So the information is a bunch of F lambdas, one for every object of D. And now where do these F lambdas live? These F lambdas live in the category of sheaves on X to the lambda. So we're going to have a bunch of these sheaves, right? And they're going to fit together. These things are going to fit together in the way you think they will under the maps inside D. Have you all pictured what the association has to be? Good. And now, but there's one additional piece of structure that I need when I look at this. The additional structure I need is what happens when I look at F lambda plus mu. So remember, this is if I have two of these objects of D, two of these sets within equivalence relations, then I can just put them side by side and say that no two of these, nothing here is equal to anything here, right? I'll just direct something's supposed to be. So this is an object of AX, X lambda plus mu. And this X lambda plus mu, well, let's look at it. It's not the product of X lambda and X mu. It's like the complement of a diagonal inside that product morally. So, but in any case, it does project down to X lambda and X mu. So I can take F lambda here and F mu here, and I can pull them back and take their tensor product. That's usually denoted by a box times. And I'm going to require that these things be equivalent. That's extra structure. Extra structure you need to write down.
Is there a natural map that you get?
No, it's extra structure.
And then it has to be probably compatible with some other stuff?
Yeah, it has to be compatible with everything in sight. So you're probably thinking, well, how the hell are you going to write this down effectively? Here's how you write it down effectively. So this is the sort of vague idea. How do you say it precisely? Well, what you have is you got X, which gives you a functor from D to script X op. So that's what X does. And then you've got AX, which goes from X op to symmetric monoidal categories. And then, well, what can you do? You can look at the Grothendieck deconstruction of this thing. So that gives you a symmetric monoidal co-Cartesian fibration, which I guess I'll call boldface A. That seems cool. A of X dot. And then this category is the category of co-Cartesian sections, symmetric monoidal co-Cartesian sections of that symmetric monoidal co-Cartesian fibration.
So what's A of boldface A?
It's the Grothendieck construction applied to this thing. If that's too much category theory for you, I can explain how this works at some other time, but this is technically how you do that. This is how you can write down a definition of all of this data with all the correct compatibilities in sort of finite time.
So an object of the Grothendieck construction is a pair of an object of D and an object of the image of D under that.
That's right. Okay. So it's a pair consisting of a lambda and an F in X in sheaves on X to the lambda. Okay, so what are the theorems? Well, the theorems are that this construction, which is very, very simple, and it's actually the natural thing that you do. Let me emphasize that. It's the most natural thing that you can possibly think of to do. In the sense that if you think that X comma, you think that this X comma AX is a natural way to talk about what geometry is, for some very loosey-goosey definition of geometry, then the natural way to extend that to these isolability objects is this. There's almost nothing else you could try. You could try and experiment with how much of the symmetric monoidality you'd want to ask for here, but that's the only place where you've got any wiggle room. This is the only natural thing you could try to do. And I claim it naturally reconstructs the theory of factorization algebras. What does that mean? That means that when you want to talk about factorization algebras, or more precisely, when you want to talk about observables on an isolability object, they're playing the role of functions in this new kind of geometry. You had this existing notion of geometry here, you're going to extend it to isolability objects. And then in that new world, the functions are now observables. Exactly the phenomenon. And so now let's look at the facts.
another approach to factorization algebras, you have this, chief under vice cover.
It enters it into AX itself. It enters in here.
Just the background data.
Well, no, it's
Factorization algebra is defined by a descent condition.
I understand, but in this definition, the co-sheaves for the Weiss topology are AX. That's what you're gonna take. I'll write it down. I'll write it down. So if you want factorization algebras on your manifold M in the sense of Castello-Guilleaume with coefficients in something, doesn't really matter what, then these things are factorization algebras in this sense. But here, what do I take for my sheaves? I actually take co-sheaves on M or the Weiss topology, which is baked in. That choice is not really an important part of the data, is what I'm saying. Or it's not an important part of what it means to be a factorization algebra.
Confused because I thought, I mean, the Weiss topology is what encodes this in that particular case. The cluster decomposition. I mean, not cluster decomposition, not probably not the right.
No, it doesn't encode the cluster. It doesn't encode where the factorization happens, right? It's just sort of there to. Well, let me. I can explain it actually. Let me show you a couple more examples. So let's look at factorization algebras in the sense of Valenson and Drinfeld. So here I was taking in something like a complex curve. And again, I'll be vague about my coefficients here. I don't care. Well, no, I won't be actually. Let me not be vague about my coefficients here. I'm going to be using D modules for this. So here you just look at literal complements of the diagonals in the scheme theoretic sense to give you these spaces here. And then here I take D modules. What about locally constant factorization algebras? This is the manifold setting. This is the sort of complex algebraic geometry setting. There's a homotopical setting. And those are factorization algebras on now pi infinity of x dot. This is now a isolability anima, an isolability homotopy type. And you look at those things with respect to, well, the only thing you can do, which is locally constant sheaves. I didn't write a coefficients here. So this does in fact reconstruct all the existing notions, or at least all the ones I know of factorization algebras, or at least all the ones I can understand, let me put it that way, in the literature. Now, but the whole point of this is to try to go further. And I'm out of time, so let me not spend too long on that. But the whole point of this was to try to make this work in generalities. So for example, are there any examples over this Farg-Fontaine curve? So can you talk about factorization algebras? And indeed, you absolutely can on this Farg-Fontaine curve. Here, I'm going to look at modules over a certain ring. Let me be vague about that for the moment. But the point is that inside here, there's a factorizable version of the affine-Grassmannian. And this gives you access to, you know, all sorts of different kinds of sheaves on the affine-Grassmannian. This is like the factorizable version of the affine-Grassmannian. And this gives rise to the factorization algebras that you want to see here. An exact analogy with what happens over the complex numbers. Okay, I think now's a good time to stop. Thank you.
Thank you very much. I think, I'm sure there are lots of questions, but so here's what we're gonna do. Please write it down or remember it, and then you sit next to Clark in the, during lunch, because Ariel Davis will give the next talk just now. So stand up and do a couple of squats, and then the next talk will start in like 1 minute. Or be really quick.